T minus 25 minutes from Sean's next meeting, but T minus 1 hour and 55 minutes from the New York C++ meetup being held at the other Adobe office, which we already have badges to because we went there a little earlier, as you heard. You're going to be speaking. Do you want to tell us about your talk and what you're going to be talking about?
Sure. I'm going to be talking about, well, this is a kind of a draft of a talk about a draft of a library about a half an idea. So, so we'll see how this goes. So I've been talking mostly with Eric Niebler about senders and receivers. I looked it up. It's more than 8 years we've been having conversations around this. And I built the STLab concurrency library, which is mentioned in the sender receiver proposal as prior work and some inspiration there. And I've had some issues with sender receivers, and one conversation that I've had with Eric repeatedly is at the end of the day, I think senders and receivers are just a way of doing function composition. So basically all that they are you're composing a bunch of functions, which then you're going to execute, and those functions describe asynchronous or concurrent operations, and you're effectively building a program and then running the program. And it's a somewhat functional language that you're building them in, but the sender receiver interface doesn't readily expose that. You've got some complicated concepts that have multiple interface calls on them for setting values and setting exceptions and setting stopped and getting stop tokens, and it's this very broad interface that doesn't look like under the hood like just function composition. And so a couple weeks ago, literally like a day less than 2 weeks ago, I had this thought about, well, if you just took a sequence of functions and stuck them in a tuple, that you could use a fold expression to execute them flat in sequence where the result of one feeds to the argument of the next, and could make that work. And so I wrote a little snippet of code to do that, and then I started to think, how do you go from there to building up the rest of the capabilities that you would have in sender receivers, and got pretty far and had some insights along the way. The work certainly isn't complete at this point, but it's got some interesting aspects to it in that the structure of these things, I call them chains. It's really just a two-dimensional tuple of tuples under the hood, and that's maintained and exposed. The structure of them is very simple, but when you want to actually do something with them, you can wrap an algorithm around them that transforms that structure into a new structure and then executes that new structure. And what that means is like in senders receivers, you would say then and hand it a lambda, and what that is in senders receivers is what is it? It's a sender adapter closure, right? So it's taking a lambda and it's capturing it in a sender, and adapting it to the sender interface and giving you back a new function in quotes, which is a sender that accepts a sender and returns a sender. So it's this complicated little thing. And in my model, then lambda expression is just take the lambda expression and append it to the end of the tuple. That's it. And then all the magic happens when you go to execute this, all the transformation to execute it. And I think there's some significant power in there. So I've shown that I can do the, transfer the execution onto other threads or other execution contexts, and I can inject in the transformation cancellation tokens and error handling. These functions are free to throw exceptions if they want to throw exceptions. All of the handling of that is handled outside and injected into the system. So that's what my talk is about, and that's the idea. And I kind of build it up from first principles, and I start with the ideas that led to me building the STLab concurrency library, and what are the problems with the STLab concurrency library, and why senders and receivers are one potential way to solve that problem. The punchline at the end is I'm not quite sure where to go from here. I've discovered some things that are broken in std.exec, and the realization that at the end of the day, this is just which we're building up as a functional language. We would like to prove that it's computationally complete. So I've nerd sniped the std.exec authors into trying to figure out how they do that inside of std.exec, and trying to fix the issues that I've raised, which are mostly around the split operation in senders receivers, which is a required operation if you want to prove you're computationally complete. For Connor, you have to be able to implement an S combinator, and an S combinator repeats a term, and that's a split.
We love that. The starling bird. We love the starling.
Yep.
K's the kestrel.
K's the kestrel.
S is the starling.
Yep.
In this talk, it'll be, I think Adobe records them. I remember seeing, or was that when Sean Baxter was at Bloomberg? I mean, hopefully this will be recorded.
It's supposed to be recorded.
And it'll be on YouTube at some point.
I'm sure at some point Sean will probably give this talk at some other conferences too.
This is true. This is true.
Yeah.
But the eager and avid listener will want to see it as soon as possible. But we were chatting about this, was it 2 nights ago on Tuesday when we were at Sugarfish? And this time you explained it, well, I think the same way, maybe slightly different details, but it made me realize that I actually, in a first edition of a different tool that I was working on at work, I did something not exactly similar, but I was trying to store views in these tuples. And like the C++ 20 and 23 views. Because at one point I was trying to like lazily build these up and then just like launch them at the end, but that ran into just like massive compile time problems, because the larger those things grow without actually, invoking them, the slower and slower the compile times get. And because I was like automating this stuff, I was doing something super terse, and then it would explode into this massive thing. So then the alternative I thought was like, what if I can just store each of these as like, a slot in a tuple or whatever of some arbitrary length. And it worked up to a certain point, but then I just ran into a mess. I'm not like a crazy template metaprogrammer, so I was probably doing some stuff wrong. But I remember like, trying to store lambdas in tuples, because like lambdas have unique signatures, and you had to stamp out a bunch of different and then you said you're using fold expressions, which I was not doing. Is there like a bunch of tricks that you're using to do this, or?
It's not much of a trick. I mean, not in my slides, but if you so if you've got a tuple of functions, and you can call std.apply to basically split those out into an argument pack, and so now you've got an argument pack of functions, and then you can take the arguments that you want to call it with, and you turn that into you capture that itself into a tuple, whatever the arguments are, and wrap that into a little struct that's got a pipe operator, and that can then feed the next function and capture the result of it as a pipeable entity. And so now you can just say my initial arguments pipe, my arguments pipe, dot, and you've got a fold expression that will execute the complete sequence of tuples flat.
I mean, it is a cute trick. I definitely think that would have been useful in my failed attempt to do that. And then I switched to Python and gave up on C++, and dynamic interpreted language. Woo! That's a lot easier, folks. Than just shit stuff on the fly.
Well, I'll admit, when I was starting to build the code, I got lost in the type signatures pretty quickly, and I was like, okay, I'm just gonna start with make it work with an any, right? Right? We collapse everything to an any, make it work with that, and then figure
halfway to Python, basically.
Halfway to Python. Yep.
It's interesting because one thing that I, and to some degree Connor, have been working on recently has been looking at how do we parallelize range pipelines. And one of the challenges with that is that if we have like a range pipeline that has a filter somewhere inside of there, we got to go find that filter and we got to replace it with some other operation that introduces some tombstone values, and then later we remove them. And there's all sorts of other optimizations that we got to do, or we have to be able to inspect the whole pipeline. And because of the way that range pipelines are built today, which is where they're nested, it's a little bit harder to do this decomposition and optimization. And, if instead of being this nested structure, if they were represented as like a tuple of views or a tuple of things that were going to be applied together, it would be so much easier.
Yeah, things to be composed instead of things already composed.
Exactly.
Right.
Yeah, because like I think maybe the realization that we didn't have was that like with ranges, the reason that they come to you already composed is because there's, that there was in the serial world, there's really just sort of one way of composing them. But actually, or sort of naively, there's just one way of composing them. But actually, you might want to do optimizations or transformations or compose them in a different way, apply some different thing to them. And so representing them in the uncomposed form, and that gives you a lot more flexibility.
Yeah, and that's what I found is you can inject, like I said, all the structure you need. And so instead of in the sender receiver model where you're pulling through a message for what happens if there's an exception and messages for stops and things like that, that interface impacts every single level all the way through the pipeline because it all has to be composed together. If instead you say, just give me the structure, all of that information can be injected after by just transforming that structure. And when the structure is flat, it's pretty simple to do. And since these are all, it's a tuple of functions, and they can be lambdas, but you could also have a type in there, which is your filter. And so now you can scan through the tuple and pull out particular types. So if you have additional information you want encoded in there, you can encode it in the type system and pull that out as part of the transformation.
I wondered too if it depends on how it was implemented, but like if you have an ability to avoid one of the worst parts of ranges, which is the errors at compile time, because like I'm even as a ranges expert, and I'm not Tristan or Eric level, but I've spent quite a bit of time playing around with ranges. Every once in a while, I remember running into my first few errors. It's just like this wall, and it's like it's not wrong. It is technically the type, and it's just this nested crazy thing. You might run into the same problem, but potentially there's a opportunity to like avoid that.
Yeah, it's potential at this point. The error message that I most frequently get is tuple doesn't support the call operator. And that really means that some piece of my tuple in my fold expression is gone, and it doesn't tell me, since it's within the fold expression, right. It's like one of the 20 things you have in this pipeline is bad.
Right.
Yeah.
And that's a pain. I've got some thoughts about how to well, there's a couple things. Right now I'm building things where everything takes, auto ... as the args, and which means you're able to build these very generic computational patterns. But that also means when you actually call it with, invoke it with 42 and something goes wrong because there's a type mismatch in the path, that you're completely lost. And so one of the things I'm playing with now is what are the trade-offs between having the developer declare the interface for the entire construct up front, so that as you append each thing, you can say, okay, if I know what the interface is, then when I append the first thing, I can see, well, will it take those arguments? And then what does it return? And when I append the next thing, I can say, will it take the thing that's returned from the previous thing? And so on. So I can type check the entire path.
Yeah, Connor, I think you make it's a very interesting observation there, and I think to do better, you have to not diagnose either when you're folding or once the thing is folded, because the problem is that the folding operation, you end up with this recursive structure, and then if something bad happens down deep in the structure, then it has to roll up the stack. And even like if you don't explicitly do that, just the way that the compiler diagnostics are going to work, it's going to tell you, well, this failed here, and and then this is the failure in the source, and then that was in this context, in this context, in this context, and it'll walk up the stack trace. But if you've got it as this linear chain of tuples, then you maybe have some other options where you can do some checking before you do the fold, where you just go through each pair and say, like, do these things, does the first one connect to the second one? Does the second one connect to the third one? And that could, I think, give you better diagnostics and give you more of the flat diagnostics that you'd get from just if you were writing like straight imperative code. So yeah, I think that has some real potential there to give you better diagnostics. I don't know whether it will help. The other challenge that I think a lot of people have with ranges is around compilation time, but and same for senders. I don't know that this helps you there per se, because ultimately at the end of the day, you're still doing the same composition. But I think it may really help with the diagnostics. It's very interesting.
I mean, I'll link in the show notes. This has nothing to do with C++, but I saw in a talk by Jose Falim, the creator of Elixir, as they have a big pipeline. It's like not even just a library. It's the whole way the whole language works. And they showed this little demo in a Elixir live book, I think is what they call it. It's like a Jupyter notebook, but they just rebranded it. And you build up your little pipe expressions. And then if you have a problem, they just like in the notebook, you can like toggle off each one of the pipes. Like if you got a functional map or a reduction or whatever, and then like there's a little hamburger bar and you can slide them around and stuff. So I was watching this and I was like, oh my God, like when you've got a problem in C++ with ranges, it's just like, a wall of template mess. Whereas over in this dynamically typed language, they're like, well, check out this little demo of debug. And like you could, as the final thing, you could pipe it to like a debug print or something, and then in the notebook it shows you at every stage like what the current value. Anyways, it was just amazing. So I'm not saying we're ever going to get to that, but there is hope out there that things can be better. And that's why we have you on the show, so we can give you a bunch of work, Sean. And
you're gonna go write a C++ committee paper, of course, and give us a full reference implementation. And
sure, and first, now that he's got me thinking about this idea, I'm going to go write a C++ interpreter just so we can do this. That'll be a good weekend project, I'm sure.
So